Skin colour patterns in fishes, amphibians and reptiles are self-organised through interactions among three types of chromatophore cells. This patterning process is efficiently described with reaction-diffusion, or RD for short, a model developed in 1952 by Alan Turing. Surprisingly, adult ocellated lizards exhibit a scale-by-scale colour pattern. Even more surprisingly, many scales switch from green to black and from black to green during the life of the animal. We have previously shown that scale colour flipping is not random, but obeys a stochastic cellular automaton, or CA for short, a computational model invented in the 1940s by John von Neumann. We have also shown that this discrete CA emerges from continuous RD because of the reduction of skin thickness at the borders of skin scales. However, can we generalize these dynamics to other species? To answer this question, we investigate 4 additional divergent species that independently evolved CA dynamics: the black and white tegu, the Gila monster, the mangrove monitor, and the Standings day gecko. In several individuals of each species, we match scales across time points and produce a space-time network of scales, which is then used to optimize parameters. In the stochastic CA, in the lens Ising, which is another stochastic model, and in the RD model. We optimize parameters by minimizing the error between simulated and observed patterns. A principal component analysis illustrates that, in real lizards, the juvenile develops towards the adult pattern positioned at the 0 error coordinate. We then show that all models generate patterns with low errors. The RD simulation, starting from real juvenile colours, produces yet a smaller error. In conclusion, the 3 models robustly predict nearest neighbour statistics, hence the general labyrinthine look of real adult patterns. We then perform the same analysis in the 4 additional species. Our results indicate that all models are good neighbourhood configuration predictors in all species, despite the substantially different motifs of their patterns. We then investigate if these various models predict not only neighbourhood distributions, but also individual scale-by-scale adult patterns. Our analyses indicate that the stochastic models generate large scale-by-scale errors, despite the fact that they excel in predicting neighbourhood statistics. This result is confirmed by the absence of correlation between nearest neighbour error and scale-by-scale error. On the other hand, RD generates a smaller error, especially when using the juvenile colours. We then sought to identify and quantify the sources of the 24% residual error. First, we reconstruct a 3D patch of ocellated lizard skin using episcopic microscopy, and construct 1,000 noisy domains that each exhibit the observed thickness heterogeneity. For each domain, we run a 3D reaction-diffusion simulation and compare the resulting pattern to the one obtained with a reference domain of identical bumps. These simulations show that given uncertainty in skin geometry, a model with perfect intrinsic predictability would still generate, on average, an error of 8.5%. But what is the source of the remaining 15%? The colour that we give to a scale is the mean value among the pixels within that scale. However, using the mean is arbitrary. If we use either the median or the mode, the colour difference is not perceptible by eye, but it is there, and it amounts to between 2 and 4%. We then show that this initial small error produces a mean error of 16.1% in the adult, explaining all of the remaining residual error. Remarkably, these results can be generalized to the 4 other species. Indeed, RD systematically generates a smaller error than stochastic models, and the gain substantially increases when using the juvenile real colours as the initial condition. We then show that in all species, the total of the RD residual error is again explained by a combination of uncertainties in both skin geometry and in juvenile colours. The exception of the gecko is discussed in the original article. To sum up, our study yields 4 major conclusions. First, cellular automaton dynamics have evolved independently in multiple lineages. Second, simple statistical models predict almost as efficiently as reaction-diffusion the time evolution of pattern statistics. Third, deterministic reaction-diffusion predicts exact scale-by-scale patterns substantially better than simpler stochastic models. This is due to the intrinsic properties of reaction-diffusion discussed in the original article. Fourth, the residual scale-by-scale error is explained mostly, if not entirely, by uncertainties in skin geometry variation and in colour measurements in juveniles. Our study indicates that reaction-diffusion is remarkably performant for predicting actual patterns without the need to parameterize the unmanageable profusion of variables at lower scales.